live. You'll be able to go home and listen to this, and so will the millions of others on YouTube. Isn't this fascinating? Okay, so we're going to start off class with this little thing that I put up here. This is a triangle of knowledge, understanding. One that I found, I guess, real quick last year or the year before that I'm going to add some stuff to here. This is what I believe is going to make you successful, okay? So, anyone ever see this before? I ask this all day long, and then, or a version of it anyway. Okay, so the idea of this is the following. Passive learning compared to active learning. If you just sit there throughout this class and not take notes, by the way, notes are good for maybe reference later, but it also is good for something else. It activates your brain more than just sitting there and listening. So if you just sit there and listen, you will probably pick up only 5% of what's going on in this class. So you don't really see anything here reading. Sure, if you read it on your own and tried to figure it out, you probably get a better chance of learning. Audio, visual, I showed you some movies to begin with, get you activated here. Demonstration, also in here is the writing part. So writing your notes down. So the act of writing actually activates your brain in a different way to solidify the stuff. So hopefully you do take that to heart, so that you get more out of this class than, you would if you weren't taking notes. But really what I do believe is the key thing is practice by doing. How are we going to practice by doing in this class? What's the thing that we're going to have to do? Anyone? How do you practice by doing in math? Homework, all right? So the non-homework doers almost never do well in any math class that I've ever taught. Okay, it's not just because their homework grade sucks them down, but it's also because their tests are terrible too because they don't practice and therefore don't solidify the content. So just be aware of that. If you're a non-homework doer, I will get on you. Those are the students that don't like me because I know you're leading to a path of failure. All right, and you are creating that problem yourself. Real big thing, though, is when we work in groups, the leader of that group, just not by selection, but just the ones that really take over and try to teach others, you really solidify the concept when you do that. So hopefully I do see some leaders in here. If you do know it, and then the act of teaching it is actually going to help you as much as it's going to help the other person, all right? Because it makes your mind think about it in a way that you can present it to someone else so it gets deeper in there, right? Further roots. So I just figured I'd start with that little concept and then actually get into the physical math concept. Oh, by the way, within that triangle, I kind of force your brain to be actively involved in a lecture scenario illegally, but lectures do still have places in this Common Core movement we have. I can pick you individually, and I will. How many students do we have in here? I'm going to actually count it off. Let me pause the movie, but that's what we're going to do. I'm going to number the students and pick them randomly as we do the notes. So let me pause the video for a second. Ah! I did that wrong. What the heck was that noise? All right, student number. What's the square root of 9? You're done. No, I'm just kidding. But why is the square root of 9 3? Because what a square root asks is a number times itself. What number times itself equals 9? So student number, what's the cube root of 27? You know that answer? 3. And by the way, I'll do this offline. Okay, do you know the fourth root of 16 then? It is 2. Most common error is people just saying 4 blindly because they see the root sign and they know the square root of 16 is 4 because 4 times 4 is 16. Wrong. You need a number times itself 4 times. So, I don't know, I see a lot of mistakes. I've taught Algebra 2 last year and see a lot of students just ignore what's called the index. And the index is the number in front of the radical, which is telling you how many times the number is multiplied by itself to equal what's called the radicand, the number on the inside. Don't worry about those terms. Actually, you probably should, but, they're silly math terms, that I guess it'd be nice to know them. Now, if anyone taking notes right now, everyone should write this down because you probably ran into this homework in the homework yesterday, and I bet you over half of you did it wrong because it's actually tricky. I personally don't like this kind of question because it is tricky for you guys. So write this down, but then write these two below it. And then we could probably answer those 2 questions first, and most of us know those answers. So let's bounce around and get another student. Chapow, hey, lucky you, student number 10. What's the fourth root of 81? Do you know that answer? Okay. Then we broke it down And 3 times 3 is 9, and 9 times 9 is 81. So 3 times itself 4 times equals 81. So now answer the next one. By the way, this negative is on the outside, so it's okay. What's the negative 4th root of 81? Student number 10 again. It's not 3. It is negative 3. So what it is the 4th root of 81 is 3, then you slap a negative on it at the end. And I do have to speed this up, so I may end the student portion of this because I do want to get a video online for the others. So what is the deal with the question that I started with that I said you better be worried about? This first question is never a plus-minus answer. All right, it's just what is the 4th root of 81? The answer is 3. And then this one's obvious. I think everyone would get this right. This is negative 3. I just put a negative on this answer. This question should be worded, name all of the 4th roots of 81, or name all of the numbers when multiplied by themselves 4 times equals 81. Everyone, what's the answer then? Plus or minus 3. So when it's annoyingly worded like that, you need to get all numbers when, in this case, multiply by itself 4 times equals 81. So be careful. It's tricky, and we have a question. I'm running out of time because of my silly little science video from a math teacher. So write this down. And then all of these things you need to separate in your brain because they're all semantics. They're details. This is actually solving an equation, which is completely different than those 3 questions that I have right there. So what you need is every single number when taken to the 4th power equals 81 again. You need every number that works for x. So with that being said, what's the answer for x in this question? Plus or minus 3. You really need to work on when do I use a plus minus and when do I not. And there are the reasons. They're all right in front of you and you need to sink it in and get it into your brain. So when you look at all of these questions right here, these ones, all 9 of these, do you use a plus minus in any of them? Actually, no. Because all of these are just simplify the radicals. That's all they say. So basically you put the sign of whatever the question started as. All right? Because they're not asking that silly little set of directions, and we're not solving an equation. So hopefully you get an idea on that and figure that out more as we go. And I'm going to forget about the asking students questions. I'm just going to go through the lecture because we have 7 minutes, 6 minutes. So what's the cube root of negative 125? By the way, what's a negative times a negative times a negative? Answer the question. A negative. So can I take a cube root of a negative and get a real answer? No time. Yes. What is the answer to the cube root of negative 125? Anyone know? Negative 5. Why? Because what's negative 5 times negative 5? No time. 25. Times another negative 5. Negative 125. So negative 5 times itself 3 times does equal negative 125. So that is the answer. And it works. So basically you can take an odd index on a radical of a negative and get an answer. You can take a cubed root, a 5th root, a 7th root of a negative, and you will get a negative answer, and it's fine. Compared to number 2. What's a negative times a negative times a negative times a negative? Positive. So what is the 4th root of negative 256? Today, you're actually supposed to say no real answer. So what is it, fake? No. What is the answer actually? What kind of form is it? Imaginary. What is the answer to this question? It does have an answer. It's just imaginary. Who knows what the 4th root of 256 is, by the way? What's the number? What number times itself 4 times equals 256? It is 4, but what is this answer in imaginary format? 4i. And what is I? I is the same thing as the 4th root of negative 1, which is the same thing as the square root of negative 1. If you know your powers of, I numbers and all that stuff. So that's what I is. It's just defined by a letter. All right? So either or, it's probably be smart to get used to this because we are going to get to that. Oops. even though you did do this last year, you did do I numbers. Let's proceed on. This is just a calculator. Find your square root button. I'm not going to waste time on that. And then for 7th hour purposes, not going to waste time on this, but find your X root button or your button that looks like this on upgraded calculators. It's a root button with 2 blanks like this. And what you can do is fill in the blanks, with the index needed. In this case, this is a 5th root. So in other classes, I gave a time and allowed you to, make sure you got the right answer. If you will, just pop open the notes tonight and then just make sure you're able to find those. If you have an unupgraded calculator, then it's an X root button. I will say one more thing to demonstrate knowledge that you should have learned last year. You can turn a radical into a fractional exponent. The power on the number is the numerator of the exponent. The index on the radical is the denominator. And then you can see through my calculator strokes that I got the same answer for both. So be aware of those math skills when you have to do such things. All right. Moving along, we got like 3 minutes. And basically what I'm probably going to do is as the bell rings and you leave, I'm just going to continue the video and talk to space. Nobody in this classroom. And then post this video online. But let's go until the bell. What's the cube root of 8, everybody? 2. So this is freedom. All right. Anything that is a perfect cube, you can bust out of that cube root. So the cube root of 8 is 2, and it's free. You don't put a radical on it anymore. 2 times 2 times 2 equals 8. Now, I'll be interested to see how many people know this. I changed colors there. Didn't activate. Green. What's the cube root of n to the 9th? It is n to the 3rd, and I'm going to explain it in a millisecond or a little bit longer. What am I supposed to do with these exponents, by the way? So if you have an idea of what to do with exponents, you know why this is the answer. You add these exponents. So what times itself 3 times equals n to the 9th? N to the 3rd times itself 3 times. That's why an n to the 3rd is freed from the radical. No more radical on it. The problem with this is u to the 5th. And because of time, I'm just going to tell you this is what you do underneath that radical. 5 doesn't go well with 3. What you do is change u to the 5th to u to the 3rd times u to the 2nd. Why? What is the cube root of u to the 3rd? Me? U. And then what's stuck inside? In jail, like you might feel? The u squared. It's just not enough to get out of a cube root. There's only a u times a u. All right, that's left over. So this is called simplifying a radical, breaking out all of the letters. Okay, so as you leave, I'm going to, in like 2 more minutes, rationalize some denominators and then post the video online. By the way, Haiku is activated. So 6 hours left and I'm all by myself talking to a computer here. As I promised, I'd rationalize some denominators if anyone takes a look at that. So like I said, what was it, 1st and 5th hour. Whenever it comes down to rationalizing a denominator, which actually I did have some written steps on that. Actually, I think another teacher made this, but I want to steal their credit. This is a rule in math. It actually just promotes you doing a skill, really more so than a rule. If you guys make it to calculus next year, this kind of is, something that's maybe not done so much. But you need to know the skill for some other things. So there's a math skill we need to get going on. So I always tell my students you should try 3 things pretty much kind of in this order, or at least try the 3rd thing last. And the last step should be trying to rationalize the denominator. So what you should do is look at your fraction. This is a square root of 3/5. Can I root it? Meaning, can I get rid of that radical simply by square rooting the denominator because it's a perfect square? And of course, in this case, no, you can't. Square root of 5 is not a perfect square, so we can't. So next thing is can I reduce it? Can I take 3/5 and reduce it so that there is no more radical in the denominator? No, I can't. So now I'm stuck with rationalizing it. Really, this is the 3rd thing that you should do. 3rd check. So how do I rationalize? I have to understand that I can rewrite a fraction and a radical as 2 separate radicals and then multiply by what is causing you the problem on the bottom, which is a square root of 5. Well, wait. First of all, let's re-explain that. First things first, square root of 5 over the square root of 5 is equal to 1. That's why this is a legal procedure for you to try and do, because all I'm doing is multiplying this fraction by 1, so it doesn't change its value. Second thing, why did I pick the square root of 5 over the square root of 5? Because in the bottom, this turns into, if you want to take this slow, the square root of 25. Rules of radicals. If a radical times a radical exists, you can take these two radicands and multiply them, and then put them underneath the radical. Same thing up here. And then the whole value of this is, if you call it that, square root of 25, of course, everyone knows is 5. And what you've accomplished is you've gotten rid of the radical in the denominator. Now, can I take this 15 and 5 and reduce them? Some people try to do that. And the flat-out answer to that is no. No, you cannot. The root keeps that in jail, so it cannot mingle with that 5 that is out of jail. Okay, so then let's go to this one. Let's do it in order, of what we have here. So, root it. Can I root it? Well, I have a square root of 12 here. Can I root that perfectly? No. But what you can do and you better do is, root it a little bit, meaning simplify that radical before you rationalize. So, as a matter of fact, you can root it a little bit. What is the square root of 4, everybody? And the answer to that is 2 for those playing at home. So I can rewrite this as this real quick, and then I can go ahead and go through a process of rationalizing. The problem with multiplying both top and bottom by root 12 right off the bat is you're still going to have to simplify the root 12 at some point. So just make sure you're aware of that. Do two things at once. The 2 over 2 turns into a 1 over 1. I'll write them just for purposes of so that I see them. And then this is just 1 times root 3 because these cancel to be 1s over root 3 times root 3, which is a free 3. So this is root 3 over 3, which I would argue does look a little bit cleaner than that. The last one didn't look so hot after you rationalized. It looked a little bit more complicated, actually. All right, so then the whole process of how do I rationalize a denominator when I have a cube root? Well, I have a cube root of n. And in a perfect world, how many n's would be underneath that cube root? And I hope to gosh you answered that you wish you had n to the third, or 3 n's multiplied together. Well, by golly, make your fantasies come true. And how you make that happen is you multiply both top and bottom. I'll write this out instead of in exponent form. By the cube root of n times n. Now, why would we do that? First of all, again, this is equal to 1. So I have not changed the value of the fraction, so to speak, by multiplying it by a form of 1. But the next thing I've done is I've introduced a perfect amount, there's that bell, of n's in a cube root. N times n times n. So this is cube root of n squared all over that free n because I've created a perfect cube root scenario by rationalizing. With all that being said, my last example before we compose the video that hopefully works is how do I deal with a fifth root? First of all, can I root it? No, you can't. Fifth root divided the fourth, not big enough. Same thing with the n squared. Can I reduce it? No, n's and y's don't reduce with each other. So I'm left with rationalizing it. So I'm going to write this like this again because it's a rule with radicals. You can split it up and they're two separate. And then in a perfect world, how many y's do you want? And I hope at home you're answering, boy, I wish I had 5 y's, or y to the fifth. Well, like I said in the last example or two ago, make your fantasies come true. First of all, it has to be a fifth root of so that these can mingle. All right, I can turn these two fifth roots into one fifth root in my mind. And if I just put a y here and I'm able to mingle these, this will turn into y to the fifth when I multiply these radicands. So, in the numerator, you end up with the fifth root of n squared y over, all right, fine, I'll write it out, but I hope you eventually get fast with this. The reason you did this is to create a y to the fifth in underneath a fifth root. So this is what happens. You've rationalized the denominator. All right. And that was all I had planned for the day. We had some technical difficulties 6 hour, and so things didn't quite work out. So we didn't get a chance to do this closure. I may call this bell work tomorrow. So get yourself ready for that little fun experience. All right. And it's been a pleasure teaching you your first